So let us begin. Am I audible?
Yes, sir.
Okay, so let us start this lecture. So in this lecture we shall discuss epimorphisms. In the last lecture, if you remember, we discussed monomorphism. It is just a dual, not dual, but a similar sort of concept than that of monomorphisms. So, so we shall now discuss in this class epimorphisms. Epimorphisms. Okay. So the definition of epimorphism is a morphism, a morphism F from A to B in a category C in a category C is said to be an epimorphism, is said to be an epimorphism epimorphism provided that provided that for all pair of morphisms, for all pairs of morphisms G and H from B to C, some other object C, where C is a C object, we have, so A to B you have F, and B to some other object C you have pair of morphisms G and H, such that you have this, suppose you have G composition F equals H composition F, it should imply that G is H. Okay. In the monomorphism case, we were taking morphisms from back end to A. Now here we are taking the pair of morphisms from B to some other object C. So, or you can say that F is right cancelable with respect to composition. That is, F is right cancellation, right cancelable with respect to composition. Okay, so as you know, the monomorphisms, they were the categorical generalization of one injective maps. These epimorphisms are actually categorical generalizations of surjective morphisms. So a fact that you can see here is, in every concrete category, in every concrete category C, surjective morphisms are always epimorphisms. Surjective morphisms are always epimorphisms. but the converse is not true in general, as we will discuss later on. So in a concrete category, surjective morphisms are always epimorphisms. Now see, it is straightforward proof. Let f from let f from A to be a surjective morphism, be a surjective morphism in C. So we show that f is EP. So for this, let you have a pair of morphisms from B to some other object C, say G and H. Be any pair of morphisms, be any pair of morphisms such that G composition F is H composition F. G composition F is H composition F. Means on the elements of A they are same. So this means what? This means for all A in A, G composition F of A equals H composition F of A. Now since F is surjective, now since F is surjective, it means for each B in B we can find, for each B in B uh, we can find A in A such that B equals F of A by surjectiveness. Now we show that G is same as H. So means you take any B in B and see what is the image of this under G. Now G of B, for any B in B, for any B in B, G of B is, now G, B is F of A here, so G of F of A means it is G composition F of A, but here it is same as H composition F of A. H composition F of A, which is H of F of A, and which is H of B. So for any B in B, G of B is same as H of B. So it means G is same as H. So this means F is EP. F is EP. So epimorphism in short we call it EP. So in any concrete category, surjective morphisms are always epimorphisms. We will see that the converse is not true in general. But before that, we will discuss some categories, some concrete categories where epimorphisms are precisely surjective morphisms. Okay. So another proposition, you can call it as a proposition. In the categories in set and vector space, here the proof is bit trivial, but in some other categories, say for example in the category of groups, the proof is a bit non-trivial. In set and vec, a morphism F is EP if and only if it is surjective. A morphism F is EP if and only if it is surjective. It is surjective. Okay, so again we have to just see that uh, EP implies surjective because surjective always implies EP in a concrete category. So proof, we need only to show that we need only to show that EP implies surjective. EP implies surjective. Okay, so let us first take the case of set. So let F from A to B be EP in set. Be EP in set. Now define two morphisms. Define G and H from B to the set 0 1, which is a set as follows. As follows. You define G of B equal to G of B. You define equal to 1 if B belongs to image of F. B belongs to F of A. Otherwise, you define it 0. 0 if B does not belongs to F of A. And H of B, you define H of B as 1 for every B, and H of B as 1 for all B in B. Then if you see that H composition F of A for any A in A, okay, so it is H of F of A. Now see here, H is sending every element to 1, so F, it is 1. It is 1. So H composition F of A is 1 for all A in A. Now G composition F of A, if you see, it is G of F of A. Now here you are getting an element in the image of A. Say it is B, but it is in the image of A. So again it is 1 by definition for all A. So this means what? This means H composition F is same as G composition F. And since F is EP, it implies that H is same as G. H is same as G. So once H is same as G, then for any, now for any, I will show that any B in B has its pre-image. Okay, or you can say that we show that B, this B is a subset of F of A, in other words. Okay, so let B belonging to B, then H of B is 1, then H of B is 1, but G of B is also 1 because H and G, they are same. Then G of B is also 1. So once G of B is 1, you see the definition here. By definition of G, B must be in F of A. So this means B must be in F of A. Okay. So B is contained in F of A. So you can say that B is same as F of A. So this means F is surjective. F is surjective. So in set, epimorphisms are precisely surjective morphisms. Now we shall apply a similar trick for VEC also. the category of vector spaces. So now let second case of vector spaces. Let F from a vector space V to a vector space W be EP in VAC. Now consider the quotient space. Consider uh, the quotient space uh, W upon F of V, and define G and H from W to the quotient space W upon F of V by, you define G of W equal to G, you take the natural mapping, natural projection map. G of W is equals to W plus F of V, and you define H of W as the zero map. H of W is F of V, which is equal to 0 of the quotient space W upon F of. Now both G and H, they are morphisms in VEC. You can see that they are linear. Both are morphisms in both are morphisms in the category VEC, and moreover their composition is also same. You can check this. Now H composition F of any V is H of F of V. Now how do we define H? We define it as we define it as zero map. So it is F of V, okay, and this V is capital V, okay. Here it is a vector small v. It is a small v, so don't confuse it. Now G composition F of any V, it is G of F of V, and so it is F of small v plus the subspace F of V. It's a coset. Since it belongs here, so it is F of V. Okay. So thus, so this means what? H composition F is same as G composition F. So by EP-ness of F, it implies that G is same as H. This is because F is EP. But G is the zero of transformation. G is the zero transformation. Therefore, no, H is the zero transformation. So therefore, G must also be the zero transformation. So this means G is also the zero transformation. G is the zero transformation. That is, now G is the zero transformation. It means what? It means G of W equals to W plus F of V, which is F of V for all W belonging to W. This is if and only if W belonging to F of V for all W belonging to W. Okay. So this means what? This means W is same as F of V. This is if and only if W is same as F of V. So this means what? This means G is surjective. So thus, no, F is surjective.
F is
F is surjective. Thus, F is surjective. So in VAC, EPs are also surjectives. Now, in group, we also have the same. Let us see this next.
सर ये सेट कैटेगरी कंक्रीट होती है?
हाँ, कंक्रीट कैटेगरी वही ना जिसमें मॉर्फिज्म्स फंक्शंस होते हैं, जिसमें जिन कैटेगरीज में मॉर्फिज्म फंक्शंस होते हैं उसको हम कंक्रीट कैटेगरी कहते हैं। ठीक है।
तो हमने कहा था ना जिनमें वो कुछ एडिशनल स्ट्रक्चर होगा, जिनमें ऑब्जेक्ट सेट होंगे और कुछ
स्ट्रक्चर,
एडिशनल
हाँ,
स्ट्रक्चर होगा।
अगर एडिशनल स्ट्रक्चर भी है तो ठीक, बट रिक्वायरमेंट है कि जिसमें सिर्फ मॉर्फिज्म जिस कैटेगरी में फंक्शंस हों। ठीक है, वो हम लिखते हैं विद स्ट्रक्चर। स्ट्रक्चर हो भी सकता है, नहीं भी हो सकता है ना, बट सिंपली
मैंने डेफिनेशन में लिखा था ना, ऑब्जेक्ट्स आर सेट्स विद स्ट्रक्चर्स एंड मॉर्फिज्म आर स्ट्रक्चर प्रिजर्विंग मैप्स।
perhaps with structure, may not be with structures, है ना। सेट कैटेगरी इज ए कंक्रीट कैटेगरी। ठीक है, मॉर्फिज्म जिस
यस सर।
कैटेगरी में मॉर्फिज्म फंक्शंस होंगे तो उस कैटेगरी को हम कंक्रीट कैटेगरी कहते हैं।
यस सर।
So let us see the group case. So another result proposition, this proof is little bit constructive. In group category, epimorphisms are precisely surjective morphisms. A morphism is EP if and only if it is surjective. A morphism is EP if and only if it is surjective. So again, just we need to show that EP implies surjective. So let F from a group G to a group K be EP in group. Okay. Now let L be the image of this. L be F of G. L is the image of F. And suppose on contrary that L is not equal to F of this, L is not equal to K. Suppose on contrary that suppose K is not contained in L. K is not contained in L. Then so there exists A belonging to K minus L. K is in A is in K, but it is not in L. Okay, now consider the set. Consider the set X equal to this set elements. So it is a type of consisting of cosets. You can say KL such that K in K a union the singleton A. Okay, so this is a set, and let Sx denote the group of permutations on X. Denote the permutation group on S. Permutation group on X. Now define a permutation G from X to X as define G from X to X as so G of we define it in this fashion G of L, because when K is 1 so it would be L, so G of L we define it A, we define G of A as L, and we define G of KL, we define G of KL equal to KL if K belongs to K minus L, if if K belongs to K minus L. Okay, so it is sending L to A to L, and KL to KL. So it is clearly a permutation. Okay, clearly G belongs to Sx. Clearly G belongs to Sx. So G is a permutation. Now define now define two mappings P and Q from K to this group Sx by for any K in K, P of K. Now P of K is here in Sx, so it is actually a permutation. So P of K of S for any S in X. I will define this map and this as I define it as KHL if S is HL. S is an element of this form. If S is HL, H belongs to K actually. H belongs to K, and I define it A otherwise. I define it A if S is A. Here actually S belongs to X. Here S is an element of X. And I define Q and K of Q of K for any element K in K. I define it as the composition. I define it as G composition P of K composition G inverse. Okay, because G is from X to X, PK is also from X to X, and G inverse is also from X to X, so it is sensibly defined. Okay, so I define these two maps P and Q. In fact, you can see that they are morphisms, they are group morphisms. Now we claim that L is the set. We claim that the set L is actually those K in K such that where the mappings P and Q they are agreeing. P of K is same as Q of K, and say this set is M. Okay, to, to see our claim, to see this, let X belong to L, then Then px of s, px of s for any s in x. By definition, it is xhl if s is equal to hl, and pxs is a if s is a. We show that p is same as q, and then on x p is same as q, and it would imply that x is an element in this set here. Means we are showing this containment. We are showing L is contained in this set. Likewise, we would show the containment from the other side. So first consider the case if S is HL. Now if S is HL, then QXS. So it is QX of HL. So it is by definition of Q, it is G composition PX composition G inverse of HL. So it is G composition PX of this G inverse of HL. Now since G sends HL to HL, so G inverse of HL is HL. So this is G composition PX of HL. So it is G of Px of HL. Now Px of HL is HL. So this is GXHL. GXHL. Again it is XHL. It is XHL by definition of G. By definition of G. Okay. So QXHL is HL, and PX this QXS is PXS in this case if S is HL. Likewise in the other case, let S is A. Let S is A. Then again see what is. Then QXA, again it is G composition PX composition G inverse of A. It is G composition Px of A of this G inverse of A. Now G inverse of A is L by definition. So G composition Px of L. Okay, so it is G of Px of L. Now Px of L is XL because L is 1L. L you can write as 1L. So it is G of L. Okay, because now G of L. Now G of L is what? G of L is A. Okay, so so in this case we are also through. So Px is, so thus Px is same as Qx. Okay, so therefore X belongs to this set. This set is M. So X belongs to M. So this means L is contained in M. Now for the reverse inclusion, for the reverse inclusion inclusion. Suppose X does not. Suppose choose any k such that k is not in M.
सर ये पी ऑफ एक्सएल एक्सएल आएगा ना?
है कहाँ पे?
पी ऑफ एक्सएल पिछली पिछली स्लाइड में,
P of
यहाँ पे पी ऑफ
हाँ
एक्सएल। सर ये एक्सएल आएगा कि एल आएगा?
एक मिनट, P की डेफिनेशन कहाँ पे है? P हमने कहाँ डिफाइन किया है? 1 मिनट। हाँ ये है ना, P K of S is KHL if S is HL and A if S is A. हाँ XL आना चाहिए, XL आना चाहिए, ठीक। हमने क्या लिखा है? हाँ ये XL आएगा, ठीक है।
यस सर।
हाँ इसको आप एक स्टेप और लिख लो। हाँ ये G of XL, लेकिन XL L के ही बराबर होगा, है ना? क्यों?
सर
क्योंकि XL में है ना? X लिया
यस
ना
सर।
आपने L में, X बिलोंग्स टू L, सो
यस
XL इज L, सो ये L ही आ जाएगा, ठीक है।
यस।
हम्म So choose K not in M. When you are taking not in M, it means P of K is not equal to Q. So this means P of K is not equal to Q of K. So this means what? Therefore KL is not equal to L. Therefore KL is not equal to L. Okay. Now PK of L. PKL, which is by definition KL, which is not equal to L, but L is G of A. Okay. And A is actually PK of A. So it is G of PK of A. Okay. But A is also G inverse L. So it is G composition PK composition G inverse of L. G inverse of L. And which is QK of L by definition. So this means what? This means PK of L is not equal to QK of L. QK of L. Okay, so if K does not belong to M, then PK of L is not equal to QK of L. Okay, what does it mean? It means K also does not belong to just 1 minute. Uh, so we have to take we are showing that now our aim is to show that M is contained in K. So we are assuming that K is not in M. So then our aim is to show that M is not in L. Okay. So does it imply that this is not in M? Yes. So we are taking K not in M. This means PK is not equal to QK. K not in M, so PK not